Welcome back, sophomores. Last time, you'll remember we learned that work, if it is defined to be force times distance, can produce a moving effect or a kinetic effect that we've called kinetic energy, which we can calculate. Or doing work can raise an object against the pull of gravity and give it what we called gravitational potential energy. Here's our summary from last time. Work is force times distance, kinetic energy is half mv squared, gravitational potential energy is magh. All of these quantities have to be in standard units, and when they are, work, kinetic energy, or potential energy are measured in joules. Today we'll get to what is probably the biggest idea in all of science, and definitely is one of the biggest handful of ideas in physics, for sure. You should be ready to take notes and draw pictures on page 82 of your notebook. Here's a person holding a 3-kilogram ball above his head. This person has done work to get it there. No more work will be done. The ball is then dropped. We're going to look at the energies at 3 places on the way down. At the top, somewhere in between, and at the bottom. At the top, the ball is not on the ground, so we can calculate its potential energy, its gravitational potential energy, which is its mass times the acceleration due to gravity times its height, which is 3 times 10 times 5. Which is 150 joules. At the top, the ball is in this person's hand, not moving, so its kinetic energy is 0 joules. And here's the most important thing for you all to do in your notes. It's to keep track of the total energy at any of these locations in your notes. You're going to do that by showing your work here and keeping track of this as the location called top, keeping track of the different types of energy and the total energy at this location in this way. The total here is 150 joules. At this location in between, it still has some gravitational potential energy, which we can calculate. Again, it's m times ag times h, which in this case has now become 3 times 10 times 3 meters high, which is 90 joules. The kinetic energy depends on its speed because it's 1/2 mv squared. We don't know how fast the ball will be moving when it's fallen this far by using energy, so we'll use old methods to find its speed. We know that at that location it has fallen a distance of 2 meters, starting from rest, accelerating because of gravity, and we want to know how fast is it going when it gets to that point. So we use our old kinematics equation number 3. And we get v squared equals 2 times 10 times 2 is 40. So that v is the square root of 40 there. If we bring that information back over to here, we can see that the kinetic energy is at that location in between when the ball is dropped and gets to that point. 1/2 times 3 times the square root of 40 squared. Square root of 40 squared is 40. Cut in half is 20 times 3 gives us 60 joules. The 90 joules of potential energy there plus the 60 joules of kinetic energy there gives us a total energy of 150 joules at that location also. When the ball falls to the bottom, we can calculate its potential energy, and now we would say that the ball, having reached this called the floor or the bottom, has a height of 0. So we can say the mass of 3 times gravity being 10 times 0 gives us 0 joules of gravitational potential energy there. Again, we want to know that if this ball has fallen 5 meters from rest, accelerating because of gravity, how fast will it be going when it gets to the bottom? And again, we can use our old third kinematics equation. Two times 10 times 5 is 100. So the final speed when this ball reaches the ground, or the floor, or the bottom, will be 10 meters a second. That means that its kinetic energy is half times its mass, which was 3 kilograms, times 10 squared. 10 squared is 100, times 3 is 300, cut in half is 150 joules. 0 plus 150 joules means that the total energy at this location is also 150 joules. And the thing to notice here is that at every location, the total energy is the same. This is a major idea in all of science. It's that as long as no other work is done on the system, in this case, as long as nothing comes along and pushes with a force for any distance on this ball as it's falling, the total energy will be the same in any location as in any other location. Next, we're going to tackle a smaller idea. It is that height, gravitational potential energy, and total energy are all arbitrary quantities, meaning it doesn't matter where we put the ground. We're going to see this in action through two examples that will look identical to the previous one, but that will have different numbers. So you should draw that person on the ledge holding the ball 2 more times. For our first example, we're going to imagine that instead of just being one person dropping the ball off the ledge, this person has taken a small child to the ledge to show them the ball falling off the ledge. I'm using that as our example because to the child, for sure, especially on the walk up to the ledge, they would want to say that their feet were on the ground, meaning that it's reasonable for the child to say that this height is the 0 meter height, or ground level. If that's the case, then the ball is at the 2 meter mark, and the ground is actually at the -3 meter mark. This is going to affect our numbers, but won't ultimately matter in terms of being able to figure out things like how fast the ball ends up moving at any location. At the top, it has potential energy equal to, again, it was a 3 kilogram ball, so 3 times 10 times 2 now, which is 60 joules. When it's stationary in the person's hand, it has no speed, so it has no kinetic energy, 0 joules, which means that the total energy of the ball at that location, according to this way of measuring, would be only 60 joules. At the location in between, we could now calculate its gravitational potential energy, and we'd pretty quickly see that since we've said that this is the 0 level for height, that it has 0 joules of potential energy there, because its mass, 3 times gravity, 10, times its height, 0, gives 0 for the energy. Its kinetic energy would be 1/2 m, which is 3 kilograms, times v squared. Its velocity, having fallen 2 meters, we could use equation 3 to show again, comes out the square root of 40. That means that the total energy here is the square root of 40 squared is 40 times 3 is 120 divided by 2 gives us 60 joules. So here, the total energy, like we would expect if we understand what conservation of energy means, has to be the same as it was at this other location, which was 60 joules. And it is, because now we've got 60 added to this 0 makes 60 joules of total energy. At the bottom, it's kind of strange, but we'd have to figure that we end up with a negative gravitational potential energy. We're going to have a mass of 3 times gravity 10 times, now we're below ground according to the child saying that they were at ground level before. This location where the ball falls to would be below ground. So it's got a height of negative 3 and its gravitational potential energy is negative 90 joules. Its kinetic energy is going to be half times its mass, which is 3, times its velocity squared. And this velocity, if you remember from the last example, ends up being 10. So half of 3 is 1.5 times 100 gives us 150 joules. And guess what? The total energy is still 150 minus 90, a total of 60 joules. For this last example, let's take the perspective of the ball. So maybe it looks like an eyeball. That's probably a little bit creepy. But if you were there, you might say that you were at ground level. If you were at ground level there, then you'd have to conclude that this location at the top of the ledge, being 2 meters below you, would be at a height called negative 2 meters, and that this cliff floor or ledge floor down below is 5 meters below you. So it's at a height of negative 5 meters. If that's the case, we can do our same energy analysis as we did before. At the top, we would have to say that we have a gravitational potential energy of 0 because our mass, 3 times acceleration due to gravity, 10, times a height of 0 gives us 0 joules. We'd also have to say that we have a kinetic energy of 0 at that location because the ball's not moving there. That means that in this scenario, the total energy is 0 joules. In the in-between, we can calculate the gravitational potential energy as 3 times 10 times negative 2 and get negative 60 joules. We can also calculate the kinetic energy, half 3 square root of 40 squared, and get positive 60 joules. And just like we learned before, the big idea again for today is that the total energy is always conserved, meaning the same in one location as it is in another, as long as no outside force did any work on the ball in between the 0 and negative 2 meter marks. Finally, at the bottom, the gravitational potential energy would have to be 3 times 10 times negative 5, which is negative 150 joules. The kinetic energy at the bottom would have to be 1/2 times 3 times 10 squared, which is positive 150 joules. And so the way that we have accounted for height in this scenario, the total energy at all locations for the ball, anywhere between the person's hand and the floor, is 0 joules. through all of these three examples, you should notice that the heights, potential energies, and total energies are all different from each other, but not the kinetic energies, because the kinetic energies are real. Kinetic energy has impact. Height and potential and total energy are just ways to keep track of what's going on. The big idea is still that total energy is conserved if you do no more work to the system. Your assignment, after we've learned these new ideas, is going to be to do some roller coaster problems to put them to use. This is page 81 of your workbook. Maybe it's your notebook. Either way, find this page, and we're going to put all of our work for this sheet on a separate piece of paper, because you really do need more space than this gives you in order to keep track of all of your energies. We'll do part A and B of the first one together, and then your assignment is to finish the worksheet top and bottom. Here's part A. We've been given that the roller coaster starts out at a height of 80 meters from rest and has a mass of 70 kilograms. If its mass is 70 kilograms, we can instantly find its gravitational potential energy is 70 times 10 times its height, which is 80, which gives us 56,000 joules. We also know that since its velocity is 0, it has no kinetic energy, meaning that the total energy of the roller coaster here and anywhere else must be 56,000 joules. Now we're going to use that fact at location B, which is given to us as being 60 meters above the ground or 20 meters below our starting height. Now we're going to be able to figure something out that we could not have using kinematics. It wasn't possible, but it's going to be pretty easy to do using what we know about energy. The big idea that you have to have gotten here is that the total energy at one location and another will be the same. So when the roller coaster car reaches this height, its total energy is still 56,000 joules. Its gravitational potential energy is now 70 times 10 times its new height, which is only 60 meters, meaning that it has 42,000 joules of potential energy at that location. This means that the roller coaster car must have picked up the difference between these two energies as kinetic energy, so that the total can still be 56,000. We could write this equation and say gravitational potential energy plus kinetic energy has to be equal to total energy, and then say that we know two of those three quantities, 42,000 and 56,000. That means that the kinetic energy must be 14,000 joules. That means that we can pull that energy account out and use that information to find the speed of the roller coaster car at this point. We're going to say that the kinetic energy is half mv squared. And 14,000 must be equal to half of 70 times v squared. 14,000 divided by 70 is 200 times 2, means that v squared is 400, which means that v is 20 meters per second. We could never have found that out using kinematics or forces. The rest of this sheet continues in much the same way, And you now know the most powerful piece of information that you can have about all the locations on the top for this roller coaster sheet is that the total energy at all the locations is 56,000 joules. That's conservation of energy.